We can also use this notation to help us come up with yet another way to represent a system of equations. So here's an additional example. And all of these have various uses, but let's take that system of equations that we were working on. And here again, x1 plus 5x3 equals 2, and x1 plus x2 plus 2x3 equals 7. And we'll extract out these coefficients in a slightly different way. So we'll take off the coefficients from the x1 variable here, 3, 1, 1, and we'll multiply that times just x1. So we'll take x1 times 3, 1, 1, and we'll add to that what we get when we pull off the coefficients from the x2, which is 2, 0, 1, times x2. So 2, 0, 1, plus, lastly, x3 times the coefficients on x3, which would be minus 1, 5, and 2. And then that would be equal to 4, 2, 7. So just yet another way that we could represent a system of equations. We could also write this out as x1 times a1, where this is a vector a1, plus x2 times a2, vector a2, plus x3 times vector a sub 3. And then lastly, we'll just call this constant vector 4, 2, 7. We'll call that vector b. So this implies that any solution to the system of equations would have to be a combination of scalar multiples of the three column vectors a1, a2, and a3. So that's just yet another way we can think about this as a system of equations and represent it. We don't really use this representation all that much, but it's just a different way to think about how we might be able to do that. In general, a system of equations can be represented in this form, where a1 through an are the column vectors of the coefficient matrix A, which we did here. We extracted those out. So we see that we get these three column vectors here. And I guess I'll just throw in one additional piece here, which is that now that we have our form ax equals b, it implies the following equivalence. So we can take a times x and say that this is equal to x1 times a sub 1. So just pulling together two different pieces here. We've got the new definition that we wrote out this way, plus our old concept of a times x, and bringing those two things together really here. So plus x2 times the column matrix a2, plus, and I'll just put a dot, dot, dot here as we go on, x sub n, a sub n. And we get an alternate definition for matrix multiplication in this particular thing. So this is essentially theorem 5 in our textbook, just so you know. Not that you necessarily have to memorize that as theorem 5, but essentially that's what they're saying in that particular theorem. So just a nice little equivalence there, and again, a different way to think about matrix multiplication. Do an example of this, I suppose, and let's take a look at that, I guess. Again, I wouldn't necessarily expect you to be able to do this, but just so you can see an application of how this works, let's take a matrix A to be 2, 0, 1 going down, 6, 4, 2 in the other column. And we'll take another matrix B over here to be 1, 4, 3, 5, 0, 2, and 1, 3. And of course, we can do our row times column bit, but using this sort of different understanding of matrix multiplication, we can define B1 to be equal to 1, 4. And we would take B2 to be equal to 3, 5. And right on down the line, B3 would be 0, 2. And B4 is a bingo. No, I'm just kidding. It's 1, 3. Then we can define A times B using our definition, or our alternate definition, if you will. A times B is going to be equal to the matrix you get when you take matrix A times B1, and then A times B2, and then A times B3, and A times B4. So each of these is a column matrix, like in Theorem 5, as we take A times B1, we get a column matrix, A times B2, we get a column matrix. The result of those matrix looks like this. So I get A, B1. When you multiply those up, you're going to get this, 26, 16, and 9. If I take A times B2, we're going to get 36, 20, and 13. A times B3 is going to be 12, 8, and 4. And then finally, A times B4 is going to be equal to 20, 12, and 7. And then you just throw all of those things into a matrix. So AB is going to be 26, 16, and 9. Going down, 36, 20, and 13, 12, 8, and 4, and then lastly, 20, 12, and 7. And that becomes your product, which is the same thing you would get if you just did our little row times column business through that entire matrix. So just a different way to do multiplication. It's not particularly useful, but essentially, it's this form that we get here is Theorem 6 in our text. Again, I'm not super concerned whether or not you memorize that as Theorem 6 or not, but just if you're looking through the textbook, you understand what's going on in that particular theorem.